Hi, and welcome to Topic 14, Part 2. So, I know you've been on the edge of your seat wondering what's going to happen when we increase how frequently we do our compound interest, right? So, we saw that daily beat out everything. So, let's see what happens. And this, I guess, is going to not be the norm, but for tomorrow, it will be what we do. So this is topic 12, part 2. All right. So as we saw on Monday when we were talking about compound interest, we have the formula that the accumulated amount, is equal to the principal times the quantity 1 plus I raised to the n. And remember that I is that nominal interest rate or that annual interest rate, right? They're called both things, and we divide it by the number of times in a year that we're going to apply the compound interest, that we're going to calculate the interest, and the n is the total length of time. Actually, it's the total number of periods, the conversion periods. So that gives us I equals N equals MT. Okay, so I think the angle on this is a little weird, but I guess that's okay. All right, so let's see what happens here. All right, we're going to do a little mathematical trick. And that little mathematical trick is we are just going to create a new variable. I'm going to call it U. And U is going to be M over R. Now notice, I is R over M. So if I want these to match, I have to take the reciprocal. So 1 over U is R over M. Okay? Now if that's true, we now can also cross multiply here and get that M is equal to RU. All right, so we're just doing 3 little quick algebra equations here on the side. Let me put a little box around them. All right, so now coming back over here to our equation, what we're going to do is we're going to replace the I. So let me go back over here and write this as the principal times 1 plus R over M, and that's the same thing as 1 over U. So all I'm doing is I am taking this R over M, which is equal to I, and I'm substituting I equals R over M, which we said is going to be this 1 over U. So it's just a little substitute that we're doing. And now the N, which is in the exponent, is N is equal to MT. So let me put that over here in green. So N is equal to MT. So what we're going to get from that is that over here, this N is going to get substituted as MT, but M is RU. So the new value that we get for N is MRT. Sorry. M is RUT. So rut. So don't get in a rut. All right. Okay, so now that we have this, what we're going to do is we're just going to group the 1 plus 1 over U, and we're going to pull this U out to the front and pull this U, and then we're going to put square brackets around that whole thing and raise this to the RT. Okay? So now we see that we've just done this little mathematical formula, nothing fancy, but what we're talking about, or what the question was, where I left you on Monday, was what happens if we want to apply our compound interest formula more frequently than daily. Well, so M was the number of times we applied our compound interest formula, right, in a given year. And daily it was at 365. So remember, daily M was 365. We applied this 365 times. Well, what about if we want to go a lot more than that? Because we noticed that we were making more money every time, right? So as M goes to infinity is really the question. What happens then? Well, as M goes to infinity, let's look over here. M was equal to RU. Now remember, the rate is fixed. It can't go anywhere. So all I'm doing is I'm taking our little equation that we came up with, our little substitution, and I'm writing it down here. But what I'm going to notice is that if M is getting really big and it's equal to this, then that means, so maybe I should say if M goes to infinity, because M equals RU, U goes to infinity. Okay, now what you may remember from last week is that we have seen this before, this 1 plus 1 over U raised to the U. Okay, and when that's the case is that the limit as U goes to infinity of 1 plus 1 over U raised to the U is E. Okay, remember when we defined E and I introduced E? That's E. So what we get is that this part in here is actually in this bracket, so that this part is E when we go to infinite number of conversion periods in a year. So this is going to E as that number of conversion periods goes to infinity. All right, and that is what we call the continuous compound interest formula. So from this, we get the continuous compound interest formula. All right, and what that is given by A equals P, so I'm just copying this previous formula, but I'm letting the number of conversion periods go to infinity, so this whole part inside the square bracket becomes an E raised to the RT. So this is what I call the PERT formula. So it's just the PERT, which is the accumulated amount is equal to the principal, right? So let's put principal is the initial amount that you invest in this account. The rate, this is the nominal or annual interest rate. And then A is our accumulated amount. And that's how much we get after T years. So remember, T doesn't have to be a whole number. We can go like 1.5 years. So this is the number of years. All right, so now I'd like to try and do an example for you. So I'm going to erase this up here. All right, so consider the accumulated amount, and let's find out what is the accumulated amount after 3 years if $1,000 is invested at 8% per year compounded. We're going to look at daily and continuously to see how much we've improved. Because that's the most we can go. We went to infinity. And we saw that infinity gave us the PERT formula. All right, so per year, 1,000 is invested. Where was I? At 8% per year, compounded. So let's first of all look at daily. Okay, so daily. All right, so what do we know? We know that P, our principal, where do we start, is 1,000. We know that daily means we're going to apply this 365 conversion period. So every single day we're going to recalculate our interest. And the time is going to be 3 years. And so we know that we're going to need that little I, which is our interest rate, our simple interest rate for each day, right? Our daily or our per conversion period. So it's 0.08 divided by 365. And then the other number that we're missing here is the number of conversion periods that we're going to have. And that N is the number per year times the number of years. So for us, it's 365 times 3. Okay, so let's put all this together into our compound interest formula, which is 1 plus I raised to the n. P times 1 plus I raised to the n. So it's 1,000 times 1 plus 0.08 divided by 365 raised to the 365 times 3, which is 1,095. So that's going to be our exponent on this. Okay, and we figured this out already. Remember that this came out to 1,271 and 22 cents. All right, so let's see how much better we're going to do now that we're going to an infinite number of compounding, continuous compounding. All right, so let's talk about continuous. So now we're going to use the other formula that we derived. We're still going to use the same stuff. By the way, this up here should have been that this is a rate of 0.08. I'm hoping that you are clear on converting the percent to a decimal. All right. So continuous, we have A equals PR. P, the principal, times E raised to the RT. So that's going to be 1,000. E, and the rate is 0.08 multiplied by 3. Okay, so make sure you can do this and put it in your calculator and get the answer that I'm getting, which is that this comes out to $1,271.25. So there you go. 3 cents over 3 years. That's not a big difference. This is why banks don't bother with trying to use the PERT formula. They use compounding daily. Not much of a difference there. And that's because we've already gotten to a pretty big number by the time we got to 365 conversion periods. So the next thing I want to talk about is that the number of times, so let's just be clear here, note that the number of times the interest is applied affects the final amount. Right? We saw that the more it was applied, the more money we were making, but it started to level off. So if you think about it, that nominal interest rate of 0.08 can't be right because we were using it in every, it's not really the real interest we made. So it's just what is the annual interest rate, but how often we compound it impacts it, what we actually are getting. So the nominal interest rate is not reflecting the interest actually accrued. So to actually compare apples and oranges, like let's say you have an account that wants to give you 12% quarterly, and you have another one that wants to give you 8% monthly. So you're kind of talking apples and oranges. How do you actually compare? So one way you can compare is you figure out what that compounding and that rate together are if you had just gotten a simple interest, and what does a rate have to be to give you that at the end. So this is called the effective rate. So to compare the effective rate, so that's our first vocabulary word of today, our effective rate, or sometimes it's the annual percentage yield is another synonym. Alright, so that's our synonym. Annual percentage yield is the simple interest rate. Oops, sorry, my elbow hit the table. Is the simple interest rate that would produce the same accumulated amount in 1 year. Okay? So we're going to call this R, little r, and then the subscript EFF for effective. Okay, so this is what the effective rate is, and I'm going to put a square around that. So let's see, how do we actually get to this effective rate so that we can compare one account offering maybe with another one. So if we think about what the simple interest rate is, it was the amount equals the principal, 1 plus the rate, I'm going to call it little RFF, and it's applied for 1 year. So it has an exponent here implied 1, but I'm not writing 1, okay? So it's just that effective rate. So now let's think about some other account. Some other account that you know about, and let's put this over here, and we're going to say that other account, it has some compound interest. So its amount is given by the principal, again, times 1 plus I. Right, so this is our compound interest formula, raised to the n. Okay? Well, what is n in 1 year? So in 1 year, remember, we're going to talk about 1 year, n was m times t. But in 1 year, t is just 1. So this is m times 1, or just m. All right? So by that argument, this is just 1 year. We're comparing 1 year to 1 year. I'm going to change this little n to an m. Okay? So I'm not really doing anything different. I'm just setting the time to 1 year. So the n, which was m times t, is m times 1. It's just an m. All right. So I've done that much. Now what? I actually want to set these equal to each other. So I want to say, if my simple interest rate, what is this effective rate here? Because think about it. Look over here. We know P, it's the same on both sides. What I don't know is the effective rate. What does that simple interest rate need to be so that these are equal? So let's go ahead and set them equal to each other. So by doing that, we're just going to say P times 1 plus, oops, got a little bit cleaned up in there, 1 plus the effective rate is equal to P times 1 plus I raised to the m. All right, so we can divide both sides by P. All right, so we're going to divide both sides by P. So divide both sides by P, they cancel out. All right, and then we're going to be left with 1 plus the effective rate on the right, on the left, and so we're pretty much done. It's just simple algebra, right? So we're going to get from that the effective rate formula. So I'll just be really clear here. This is what's left on the left, and on the right we have 1 plus I raised to the m. Okay, and we're trying to solve for this. Okay, so by now you've done a lot of this kind of algebra. Hopefully this is not a mystery. So what we're going to get is the effective rate. The effective rate of interest formula. Right? So all we're going to say is then that the effective rate is 1 plus I to the m minus 1. Because we're going to subtract that 1 from both sides, right? It's minus 1, minus 1. And that's how we get this formula. And that's an important formula that you're going to be using not only in the homework, but you need to know it. Because that really is a key formula for trying to decide, like let's say you become a financial advisor and you're trying to tell someone which is the better of two accounts. How are you going to figure that out? You're going to be looking at a lot of factors, but certainly one of the factors is how they compare actually and what the interest they pay are. Okay, so let's try an example of this. So suppose that you have two accounts. Which of the two accounts pays more? Which of these two accounts So the first account, so let's call it account 1. So option A, it's going to pays 8% quarterly. And account 2, it pays 12% semi-annually. All right. So how do we decide which of these two? We know that the more frequent you apply the compound interest, the more money you make, but it's paying less. So these are kind of pulling in opposite directions. So we can't really compare these. So what we're going to do is we're going to make both of these figure out what their simple interest rate would be for 1 year. And that is our effective rate, or it's what we call the annual yield. Okay, or annual percentage yield. Okay, so let's go ahead and we're going to apply this formula twice now. So on the left-hand side, the effective rate is 1 plus I to the m. So here, because this is quarterly, right? Remember we talked about this? M equals 4. Right? And so that means that our I, let's go ahead and actually, let me erase this. And first of all, let's figure out what our I and our M is. So we figured out M. We know I is 0.08 divided by 4, or 0.02. So our annual effective rate is 1 plus 0.02 raised to the 4th power. Okay, and that's equal to, I need a calculator. Assistant, I need a calculator. I feel I usually use my phone. I can't use my phone. Can I use your calculator?
Yeah.
Okay. Alright, so on this side, we're going to do the same thing. Okay, semi-annually, do you remember that? Semi-annually is M equals 2. That's every 6 months. Okay. And here, our I is that rate, 0.12 divided by 2, which is just 0.06. Okay. So, this effective rate on this one for account 2 is 1 plus 0.06 raised to the 2nd power. Alright, so here we go. Ta-dum, ta-dum! Which is better? Okay, on the left, I'm going to go 1.02, and I'm going to raise it to the 4th power. And I get that this is the effective annual percent yield, the effective rate, is 1.0824. Alright, and over here on account 2, I get 1.06, and I'm going to raise that to the 2. And that is 1.1236. Alright, so even though it's just twice a year, the higher rate semi-annually is going to pay more. Oh, in both of these cases we forgot to subtract 1. See, you guys can't get those bonuses because you're not live with me. We have to subtract 1. And so this is 0.0824 versus 0.1236. Alright, so we see that in both cases, applying it more continuously, the effective rate if you had a simple interest, it had to be a higher rate to match the compounding that was going faster. But it didn't, the quarterly wasn't fast enough to outbeat this one. So let's try account 3. What about if account 3, and it was applied daily, but the rate is still 8%. Let's see if how that compares to account 2. So M here is 365, and I is 0.08 divided by 365. So our effective rate is going to be the 1 plus I, which is the 0.08 divided by 365, raised to the M. M is 365 minus 1. Alright, so let's see what that gives. Excuse me, I gotta do 0.08 divided by 365 first, and then add to that 1, and then that whole thing is raised to 365, and then that whole thing gets 1 taken off of it. and I get that this comes out to 0.0833. So really that higher rate at 12%, even though it was twice a year, it still beat it. This is a 8.33% versus a 12.36%. Okay. All right, now we're going to talk about something that sounds complicated, but it's really not complicated. And that's the present value. So let's talk about getting the present value. All we're doing here is changing what we're solving for. So we've done this before. When we chose a variable and we had all these equations that had all variables and you had to pick the variable you're going to solve for, and you get the variable by itself on one side of the equal sign and everything else on the other. That's all we're going to do here. Okay. So let's start out with what we know. So first of all, the present value, by the way, is that initial principal, because the amount, the accumulated amount, is some amount in the future. All right, so let's start with what we know. Start with that compound interest formula, right? And we know that it's 1 plus I raised to the n. Okay, and just remember, right, I equals R over the number of conversion periods, and n is the number of conversion periods times time. Okay. Now, all we're trying to do is solve for p. That's it. That's all present value is. Just solve for p. Alright, so no big deal because we've been practicing exponents and all this stuff, so we can do this. We're going to divide both sides with 1 plus I. We're going to, what's p multiplied by? This whole thing, 1 plus I raised to the n. So let's just divide by 1 plus I raised to the n and get rid of it. Remember, this is going to be a disguised form of 1. Let's put this on the side, 1 plus I raised to the n. All right, we know that this is a disguised form of 1. Boom, boom, gone. All right, so now what do we get? I'm going to just flip the way I write it. I'm going to get p equals a over 1 plus I to the n. All right? Now, the part that seems so mysterious, but I know you guys know this already, is that we can just pull this denominator into the numerator by applying our exponent rules on that n. So what do we do to pull that up? We just change the sign on it. 1 plus I raised to the negative n. All right, so that's our present value given some amount in the future and some amount of time in the future. So, for example, a good question might be, well, I need, I don't know, make up a number, $80,000 to go to college in 4 years. So the time would be 4 years in the future. The amount I need in the future is $80,000. And let's say I can find an account that pays a certain amount. So then my question is, well, what do I do? Well, I just need to know how much I need to invest now. So, I don't know. I guess that's the question. Where are you going to get it? Your uncles, your aunts, your grandparents, wherever. Anyway, but that's how you figure out what you need now if you're trying to meet a target amount. Okay? So, let's do an example of that. How much should we deposit in a bank? Paying 6% per year. So for me, the way I think about this is if I want to buy a boat, and I know how much money I have now, but I know how much I have to kind of do all the math, and I need to know what I need to start depositing now so that I can have a boat at some point. Okay. Compounded monthly. I found this account. It pays 6% compounded monthly. And what I want is that in 3 years, the amount will be $20,000. So what do we know? We know our rate is 0.06. We know that we're applying this monthly, so our M is 12. We know that our simple interest for each conversion period is 0.06 divided by 12, right? And we know that the number of times we're going to be applying this compound interest formula is 3 years and 12 times a year, or 36 times. Okay? So, to get 20,000 in 3 years, what do we need to invest now? So P is the 20,000 multiplied by 1 plus 0.06 divided by 12 raised to the negative 36. Okay? So you can think of that as 20,000 divided by 1 plus 0.06 divided by 12 raised to the 36. Okay? And if you do that in your calculator, that comes out to approximately $16,712.90. Okay? So that's how you get the present value. It's just solving for the principal. Alright, so you can imagine by a very simple, similar, analogous argument, you can get the present value for something that's that has continuous compound interest. So I'm just going to say present value for continuous. Very similar. For continuous compounding. Interest. Actually, the formula is even a little bit easier because we have A equals P, our PERT formula, and we want to solve for P. Alright, so we're going to divide both sides by e to the RT. So e to the RT divided by e to the RT. Alright, so there we go. We have a disguised form of 1 again. E to the RT over e to the RT. That's just 1. So that means P equals A. E to the RT, I'm going to pull it up and put a negative in front of that exponent. That's how I pull it up. So there's my present value formula for continuous compound interest. Alright. So this is where we can think about maybe how to solve. Now we've learned a lot of these formulas for compound interest, continuous compound interest. And we can solve for all the different parts of the equations because we know logarithms. So logarithms is how we solve for things that are in the exponent, like time. So I'm going to do an example of that. So our principal is $10,000, and our goal that we need is $15,000. So an accumulated amount of $15,000. The rate that we can get, the best we can find for any rate we've been looking around, is 12%, compounded quarterly. And this is, after we did the effective rate to compare, to make sure we're comparing apples to apples and not apples to oranges. And we know that compounding quarterly means there's 4 conversion periods in 1 year. Okay, so how long do we have to wait till we have our $15,000? Okay? Maybe there's something nice you want to buy, you want to know how long you're going to have to wait in this account. So first of all, we're going to need to get our I, which is 0.12 divided by 4, or 0.03. Okay? Now we just go ahead and plug into our compound interest formula. We have $15,000. So actually, let me just remind you what that is real quick. Hopefully you have it memorized by now. A equals P times 1 plus I to the N. Okay? The only thing that we're going to do different is because we're actually trying to know how long, we're going to change N. Remember, N was M times T. So let's convert this N to M times T, and that M we actually know is 4. Alright? So what we want to put in everything we know, because the only thing we're not going to know is the T. That's the only way we could answer this question. So we have 15,000 is where we want our accumulated amount to be. We start out at 10,000. We put in the 0.03 for our interest rate for each conversion period, and we raise this to the 4t. All right, so now we need to solve for t. Okay, so we're going to solve for t. But t is an exponent, so already, even before I get anywhere, I know I'm going to have to take logs. All right, unless I'm lucky and I get that matching base special case, which I don't think I'm going to get. Okay, so I divide both sides by 10,000. Alright, so 15,000 divided by 10,000 is like 15 divided by 10. That's just 1.5. So 1.5 equals 1.03, because I'm just adding 1 plus 0.03. Raise this to the 4t. Okay. Now that I'm looking at that, and I want to get this t out, I can take the natural log of both sides. You can also do log base 10, it doesn't matter. The base of the exponent is 1.03, and we don't have that on our calculator. So we're going to just have to pick a base. So I'm going to pick natural log. So I'm going to take the natural log of both sides. Okay. Now I'm going to take advantage of my exponent rule that's going to pull that 4t out. That's the entire reason I'm doing the logs, is because of that rule. That rule is so powerful. So what do I have? I have the natural log of 1.5 equals 4 times t times the natural log of 1.03. Okay, now look at what we got here. We got a number 4. We got a variable we want to solve for, and we got another number. ln of 1.03 is just a number. All right, so let's just solve for t. So we're going to divide everything else that we want to get rid of. So divide both sides by 4 times the natural log of 1.03. This is a disguised form of 1, right? The 4 over the 4, and the ln of 1.03 over the ln of 1.03. And we're going to divide both sides by that. If not, it's no longer equal. Right? So now we have that the time is this ln of 1.5 divided by 4 times ln of 1.03. What is that equal to? I cannot seem to get my calculator to turn on. See if you can beat me and tell me how much time this is. All right, it's approximately 3.43 years. Alright, did you get that? Were you able to match
Yep.
me? Alright. Okay. If the battery holds out, I'm going to do one more example. So here Jane wants to consider two investment options. I think this is a lot like one we already did. Okay, the first one is a CD, certificate of deposit. It matures in 12 years. And it pays a rate of 10% compounded daily. And remember, we already figured out that compounded daily is almost as good as continuous compounding, right? Or the second option is she can purchase a zero coupon CD. That triples her investment in 12 years. Okay. So which pays more? All right. Well, the first one, we have a rate of 0.1. We have a conversion period of a day. So we have 365 conversion periods in a year. We're going to apply that for 12 years, or 365 times in a year, and that's going to give us 4,380. So this one is going to give us an accumulated amount of some amount P, whatever our principal is, multiplied by 1 plus 0.01 divided by 365, raised to the 4,380. Alright, so now this part, we don't know what the principal is, but we know this part. We have all these numbers right here. So we can put all those numbers in a calculator, and we get that this is whatever the principal is times the number 3.32. Okay? Option 2. In 3 years, P becomes 3P. Right? So what's more, 3.32 times P or 3 times P? 3.32 times P is more than just 3 times P. So you want me to give you 3, like think about how much pizza, you know, I don't know, how much you get paid, you know, more is better. So option 1 is better. Okay, so that's the end of topic 14. And tune in to topic 15, where we talk about annuities, which is an interesting concept, very, very related to what we're talking about here with compound interest.